In this section, we'll be talking about mechanical vibrations. So as before, we have the function for external force in a mass spring system is the external force is equal to inertia times the second derivative of y with respect to t plus the damping constant times the first derivative of y with respect to t plus our spring stiffness constant times y. Now, for reasons that will become clear later, we will write this as F naught times cos of lambda t. So we're breaking up this external force into a product of F naught times cos of something is equal to m y double prime plus b y prime plus ky, where F naught and lambda are non-negative constants, and b squared lies somewhere in between 0 and 4mk. And so that means this system is underdamped. The solution to this equation is the sum of a particular solution and a general solution. So from before, we know what the general solution is, the homogeneous solution. This is from the last video, where a and phi are constants. To determine the exact solution, y sub p, we will use the method of undetermined coefficients. Based on the non-homogeneity, that's our value that isn't 0 on the other side of the equation, our F naught cos lambda t, we know that the solution will take the form a1 cos lambda t plus a2 sine lambda t. And that's why we chose to put this cos term in here. So it wasn't just some constant. So it would give us a direction for our solution. Well, we take the first couple derivatives here. So we've done this many times, but just make sure your negatives are all in the right place. Like cos becomes negative sine, sine becomes positive cos, negative sine becomes negative cos, and cos becomes negative sine. Then we set F naught cos lambda t equal to m times the second derivative plus b times the first derivative plus k times the third derivative. Now, we're going to break this up to the best of our ability so that we have a cos term and a sine term. Now, you know how this would go. We would set this as 0 times sine lambda t plus F naught times cos lambda t. And then we would say 0 is equal to this, and F naught is equal to this. That would take a lot of steps, and we'll just skip straight to what the values actually come out as. So we get A1 is equal to F naught times K minus M lambda squared divided by K minus M lambda squared, all squared plus B squared lambda squared. A2 actually ends up having the same denominator, which is very nice. The numerator is F naught B lambda. So our solution YP of t is equal to this A1 term times cos of lambda t plus, there's our plus sign kind of hiding there, the A2 term times sine lambda t. So we've done a little bit of factoring there to keep this F naught over K minus M lambda squared all squared plus B squared lambda squared over here. But this is our solution. Now, we can simplify this a little bit, and it's going to be using our method from the last video about converting things that are in a form of something times cos plus something times sine into our A sine lambda t plus phi form. So A, if you'll recall, is equal to the square root of C1 squared plus C2 squared. So that's where we're getting these values from. K minus M lambda squared, that's our C1 squared, and B squared lambda squared, that's our C2 squared. you can see those values right here. Oh, and more clearly, right here. So to be completely 100% correct, we will need to bracket this better. Because cos is being multiplied by that entire bracket, k minus m lambda squared. So I hope that doesn't cause any confusion. We should have actually bracketed like so. Okay, now we can substitute this value in right here. And the reason we do that is this square root here cancels out with this sort of, and we're left with the square root in the denominator. So it greatly simplifies things. So this is our y sub p of t. And of course, we remember our rule for tan theta, it's just a1 over a2. So that's k minus m lambda squared divided by b lambda. Combining our two equations, the homogeneous one and the particular one, we get this entire solution, our general solution. Now the general solution is made up of a transient part and a steady state solution. The transient part will disappear as 10 goes to infinity because it just tends to 0. So that's this part here. That's the transient part. And the part we just solved for is your steady state solution. Okay, now we'll do an example. A 5 kilogram mass is attached to a spring of stiffness constant 36 newtons per meter. At time t equals 0, an external force of 10 cos 3t newtons is applied to the system. The damping constant for the system is 4 newton seconds per meter. Determine the steady state solution to this system. So it's not asking for the entire solution, it's only asking for the steady state, so not the transient part. Well, we're going to plug all our values in. We had 5 as a mass, 4 as a, oh, lost the word. 4 is the damping constant, that's the word. 36 is your spring stiffness constant. And our external force is 10 cos 3t. Now we take all this information and we put it into the steady state solution. So scrolling back to take a look, that's plugging in k, m, lambda, f naught, and everything. So this is actually going to simplify greatly because in this square root in the denominator, 36 minus 45 is -9. Square that, you get 81. That just ends up being the square root of 225 because 144 plus 81 is 225. And that's just equal to the square root of 15. So we get 10 over, oh, sorry, that's not the square root of 10. Of course, the square root of 225 is 15, not the square root of 15. There we go. And 10 over 15 is equal to 2 over 3. Perfect. And that's how we got 2 over 3. So this is our solution. The only thing we're missing is that theta value. You'll notice that for this section, we've moved from phi to theta, but it doesn't matter what you call it. Tan theta is 36 minus 45 over 4 times 3. Well, where is that coming from? Remember, that's just a1 over a2. So k minus m lambda squared divided by b lambda. So we're just plugging values in. So we get -3 over 4 as our tan theta, but importantly, the negative is in the numerator and the positive is in the denominator. So remember that tan is just sine theta over cos theta. So the numerator, the sine, is negative, and the denominator, the cos, is positive. So that means we're in the 4th quadrant. If you want to have a negative sine and a positive cos, you're right down here. So that is still part of the rightmost portion here. So we can just take the arctangent. So that value is negative 0.64. So our steady state solution is approximately 2/3 sine 4t minus 0.64.